All right, good morning, everyone. Welcome to my talk on evolutionary architectures. I touched a little bit on this subject yesterday in my keynote about yesterday's best practice as a way to fix this problem of yesterday's best practice. Today, I'm going to do a deep dive and talk a little bit about evolutionary architectures and software. This is a book that I'm currently working on with two other people, Rebecca Parsons, who's the CTO of ThoughtWorks. She's a computer science PhD and has had some experience in the evolutionary biology world. Pat has written a really fantastic book for tech leads, and he's been spending a lot of time thinking about the intersection of people and teams and architectures, and we realized really early on that to talk about evolutionary architectures, you have to include team structure and team dynamics. And I've been talking about different aspects of evolutionary architecture and emergent design for the last few years, and so we've decided to get together and pool our IP and build some new IP around this idea of architectures that can evolve in a graceful way. Now, many of the ideas in this talk are not brand new, but it's a different perspective on architecture that maybe you haven't had before. One of the goals that we have in building this IP around evolutionary architectures is to add adaptability as one of the ilities that we talk about when we talk about software architecture around all these other ilities. And one of the main reasons that we're focusing on this right now is because we believe this is really important because of the inability to really do long-term planning in the software architecture world. This has been a problem that has plagued software architects and particularly enterprise architects for a long time because of the fundamental nature of the way the software development ecosystem works. It exists in a dynamic equilibrium, meaning that everything's in a nice equilibrium right now in the way that all the tools and techniques interact with one another. But the problem is that new things will hit this equilibrium in an unexpected way, and what happens is when a new thing hits this equilibrium, it reaches a new dynamic equilibrium that was different from the one before. A good example that we saw of this in recent history was Docker showing up in our ecosystem. And once Docker shows up, nothing's ever going to be quite the same again because you have to take that into account as you start thinking about planning your architecture and your engineering practices and how you're going to deal with software. And this is a big problem in the software world because if you're an enterprise architect and 2 years ago you made a 5-year plan to plan resources and allocations and business strategies, et cetera, and you didn't accommodate for something like Docker coming along, you can take that 5-year plan 2 years in and throw it away because the very foundation that you're planning against is always shifting. And that's a big problem because you can never predict when the shift's going to happen and you can never predict what outcome that shift is going to have. And so we think we need to get better at building architectures that can survive that shift more gracefully with a lot less expense to make changes to them. So let's start with our working definition of evolutionary architecture, and I'll explain some aspects of this as we go along. An evolutionary architecture supports incremental guided change as a first principle along multiple dimensions. And let me explain different parts of this, and I'll first talk about this multiple dimensions part of this definition. So when you look at software architecture, you're really looking at a perspective on a piece of software because you can think about different kinds of architectural perspectives on a piece of software. Now, we're mostly developers and architects, and so when we talk about architecture, we're mostly talking about the technical architecture, which are things like architectural patterns, how the components are fit together, how they get deployed together. The technical architecture also includes things like transitive dependency management, frameworks and libraries, and how those things fit together. So this is the technical architecture perspective on a bit of software. But we're starting to call this the theory of relativity of software architecture because every perspective on architecture requires a context. And of course, the context here is the technical architecture of how those pieces fit together. But for a given piece of software, you can also talk about the data architecture. which is how all the data elements work together in relational databases, how tables exist and how they're related to one another, how those things should shift and change over time. It's hard to read the subtitle of this book, but the subtitle of the Refactoring Databases book is Evolutionary Database Design. And you'll notice that goes hand in hand with the idea of an evolutionary architecture, is getting your data involved in the same kind of evolutionary cycle. And so that's a completely different perspective on architecture than the technical architecture. But you can also think about the security architecture of your piece of software, how to prevent things like cross-site scripting. And this is a good example of a really cross-cutting concern, because this may have impacts on your technical architecture and on your data architecture, because it'll make changes in the way that you implement those things to take account for this security perspective on architecture. And these perspectives on architecture are not fixed or static either, because a few years ago we picked up a new perspective on architecture, which is the domain perspective on architecture, largely driven by this really influential book, Domain-Driven Design by Eric Evans. We started now talking about how the things that we create live inside our architecture, this domain architecture, particularly this idea of a bounded context that came from domain-driven design. In fact, in many ways, you can say that the microservice architectural style, which is so popular right now, is really just the combined logical ideas in domain-driven design added to the engineering practices of continuous delivery to create this very domain-centric microservices kind of architecture. So let's talk for a second about the evolvability of architectures at the technical architecture level first, and then we'll talk about some of these other perspectives in just a second. And so we'll start with the degenerate case of no architecture, which is colloquially known as the big ball of mud architecture. And this is a picture that I captured from a project that I worked on. This is a visualization from a tool called X-ray. The little tiny sub-pixel sized dots that you see on the perimeter here are classes, and the lines are the connections between those classes, and the stronger the line, the more connections there are. This is a good example of the kind of architecture that you don't want to have, because if you try to make a change to this architecture, let's say I want to change the way we access data in this architecture, the ripple effects is going to make it really, really hard to make changes to this architecture. And so when you look at this from the perspective of can I evolve this architecture, there are 0 dimensions of evolvability in this architecture, because any change is going to have rippling, unexpected side effects in lots of other places. And so let's look at a more traditional, more common kind of, in many ways, default architecture, the layered architecture. We break things down into presentation, business, etc. Here we have one dimension of evolvability, which is along the technical architecture dimension, because we can now swap out layers without having a huge ripple effect on the other parts of our architecture. Now notice I have 4 layers here, which means I have 4 opportunities for evolution, but all along the same dimension of evolution, which is along the technical architecture dimension of this piece of software. So let me talk about this distinction between opportunities versus dimensions for just a second. So this is a really common pattern in layered architecture where each of those layers is closed, meaning that all requests have to go through all of the layers to get to one of the layers within your architecture. So you can't just make a request directly into the middle of your architecture. It has to flow from top to bottom. Then a really common variation of this layered architecture has something set up like this. And there's a little anti-pattern that lurks very often in this world. How many of you have a layered architecture like this, but for one of the layers, for at least some of the requests, all that layer does is basically do a little data transform and pass it on to the layer below, because there's nothing really for this layer to do. This is what's referred to as the architecture sinkhole anti-pattern. Because you have a layer there because for some things you need to do something and for other things you don't need to do anything. And so a common solution to this architecture sinkhole anti-pattern is to take the optional layers and make them optional and make that an open layer. So in this version of the layered architecture, I can call through the services layer if I need to, but if it's adding no value, I can call directly from the business layer to the persistence layer because that services layer is now an open layer. So this is the solution to the architecture sinkhole anti-pattern, but I've actually harmed my ability to evolve this architecture. I still have one dimension of evolution, but now I've cut down on the opportunities I have to evolve this architecture. Because notice that to a large degree, particularly in layered architecture, the ability to evolve it has to do with your ability to swap out layers, which has to do with how coupled they are to other layers. And by creating an open layer here, I've increased the coupling for the persistence layer. Because now, if I wanted to swap out the persistence layer, I have to worry about both services and business, so I have less isolation of concerns here, still along a single dimension, but now I have fewer opportunities to evolve this architecture. So let's look at a completely different architectural pattern, microkernel. This one also has one dimension of evolvability because I can add new plugins and evolve the behavior that way, but it is along that dimension. Now, these dimensions are not always strictly just in technical architecture. Because think about REST, and in particular level 3 REST, the hypermedia version of REST. Because in that version of REST, the idea is when you make a request to some resource, part of the response that comes back from that resource are the next links you can follow for the next steps in that business process. And of course, you pick a resource there, which gives you a response, which gives you links you can follow to other potential steps of this resource. So this actually sits on top of the technical architecture. This is kind of in the workflow architecture dimension, but this still gives you one dimension of evolvability. You can now change the subsequent steps in a workflow by changing what links get sent back as part of those resources and be able to make changes that is invisible to the client from the server side. But remember that domain perspective I was talking about before that we most recently picked up around software architecture? Think about the layered architecture. Where does customer live in the layered architecture? Well, part of customers in the presentation layer, and part of customers in the business layer, and parts in persistence, parts in the database. So from a domain perspective, we have 0 dimensions of evolvability here. In fact, from a domain perspective, this is no better than the big ball of mud. Because when I want to make changes to customer, I'm going to have to make changes in a bunch of different, seemingly unrelated places. They're obviously related around the technical architecture, but from a domain standpoint, this is a really hard place to make changes because I have to coordinate across all those layers. And that's why the microservice style of architecture is different. Because the focus in microservices, one of the main philosophical thrusts in the microservices world is this idea of a bounded context, that each of these services reside inside its own bounded context, which means that from a technical architecture standpoint, the dimensions of evolvability here are n, where n is the number of services that you have. Because notice there's no coupling between these services. That's another strong principle in the microservices world. There's 0 coupling between each of these domain entities, meaning that I can evolve the technical architecture for any one of these without having any effect of the technical architecture of the other ones. And so those are independent of one another, so I now have lots of dimensions of evolvability. This is a good example of an evolutionary architecture. And this is why we talk in our definition about multiple dimensions as a first principle along multiple dimensions. Because I will argue that the entire purpose of software architecture to begin with is to allow evolution along at least one dimension. That's why we don't build big balls of mud anymore. We build layered architectures or microkernels to get that level of evolution. What we're interested in are architectures that allow you multiple dimensions of evolution because those, it turns out, are much more evolutionary. Now, one of the interesting things about architectural patterns that's not true around things like design patterns is composability. Because architectural patterns compose really cleanly inside one another. For example, let's say you have a microkernel architecture. Maybe this is a business rules engine that is designed with this microkernel style architecture, and you can add new business rules via plugins. This may be one of the layers in a layered architecture. So maybe your business layer is implemented using this rules engine, which is a microkernel architecture, and this layered architecture is in turn one of the implementation details of a microservice architecture. And so notice these architectural patterns will compose inside one another very often quite cleanly, and by composing them together you actually increase the opportunities for evolution, because in this case, obviously I can evolve this guy any way I want, but inside here I could change out one of the layers, or I could change out some of the behavior within one of the layers because of the composability of architectural patterns. So that's the first part of my definition. An evolutionary architecture supports incremental guided change as a first principle along multiple dimensions. That's the dimensions part. Let's talk about incremental change next. So when you have a mature architecture, a service-based architecture or microservices architecture with really good 21st century DevOps practices and continuous delivery, very often you see this incremental change pattern implemented, where we've separated component deployment from feature release. Many of you, when you deploy components into production, you're also releasing those features at the same time, but you can decouple those things, and it's quite common in particularly the continuous deployment world. I don't want to release features as they come out, but I do want to get the components into production as quickly as possible to make sure that they monitor correctly and they log correctly and they play nice with all the other components and don't eat up resources, et cetera. And so it's very common in this world that you deploy components without necessarily releasing the features inside them. And then at some point later, using some mechanism like feature toggles or routing, you turn on those features and make them available for people. What this allows you to do, having this isolation, is to run a couple of different services that are almost the same side by side, because in this world, applications really consist of the routes that you choose between the services that you have implemented. And this is this idea of incremental change at the architectural level. And this is one of the superpowers that you get when you choose the microservice architectural style. So let's say that you run WidgetCo. It's a company that sells widgets to people, and you have star ratings where you can star rate widgets, or you can star rate shipping methods or customer service reps. So you have a star rating service that handles that inside your architecture. And then one day you release a better star rating service that lets you do half-star ratings. And you just make it available in your architecture, but you don't force anyone to move to it, but the opportunity is down there, and so these other services in their own time frame, as they want to improve their star rating ability, start routing to the new improved star rating service, and over time more and more people route to this new star rating service until no one's routing to the old one anymore. One of the magic tricks that Netflix taught us in the microservices world is that you monitor not only services, but also the routes between services, and any service that you find that no one is routing to anymore, you automatically disintegrate it out of your ecosystem. So this is incremental change at the architectural level. Notice what I did here was I improved some functionality and put it live alongside the old functionality. I didn't force anyone to move to the new one. I just made it available, and people in their own time evolved to the new one because they wanted that new capability and those new characteristics. And then when the old one wasn't used anymore, we automatically garbage collected that away. This is incremental change at the architectural level. And of course, this is one of the magic superpowers you get with microservices that is somewhat offsets all of the operational stuff you have to do to get that level of isolation. This is the benefit you get from it, is the ability to make really small little changes at the architectural level. In fact, this is an interesting characteristic of microservices, because for a long time we said that the pieces in architecture are the things that are hard to change later. That used to be the definition of software architecture. But it turns out if you design change into the architecture, it's not expensive anymore. And that's exactly what happened in microservices is we designed the ability to do incremental change into the architecture, and it's not so expensive or hard to do anymore. So that's the incremental change part of this definition. Let's talk about guided change. And this is where we're coming back to the evolutionary biology metaphor and this idea of fitness functions. A fitness function in evolutionary biology describes productive success and is equal to the average contribution to the next generation's gene pool. But when we're talking about this from a software standpoint, what we're talking about are ways to guide the pieces of our architecture so that it doesn't violate rules that we want to have in place. So what we really want to support here at the architectural level is the ability for each one of these architectural pieces to evolve in whatever way makes sense for the business case they're trying to solve, or whatever business abstraction they're working on. But that doesn't mean we throw away things like performance or scalability or things like security auditing. All those are still important parts of our architecture. What we're trying to do in an evolutionary architecture is capture those things as fitness functions. And so a fitness function in this world is some sort of objective result that evaluates one of the quality characteristics of your architecture. And so these may be metrics. Maybe you have a fitness function in place that says we don't want our test coverage to fall below a certain level. Or maybe you have a fitness function in place that says our cycle time, which is a measure of engineering efficiency, should never grow more than 3 hours because we're doing continuous deployment and we want to make sure we have a really tight feedback loop. This may be some tests. I'll show you some examples of fitness functions implemented as tests in just a second. But these are basically the guide rails that we're building into our architecture so that we don't violate some of the core things that we need to support. And so what have traditionally been called non-functional requirements or quality of service kind of requirements become fitness functions in this architecture, because what we want to do is take those things and automate the running of these functions so that we can evaluate the fitness of our architecture on an ongoing basis. And I'll show you some examples of fitness functions in just a second. So that's our working definition of an evolutionary architecture. It's one that supports incremental guided change as a first principle along multiple dimensions. And that now brings us to the agenda for this talk. The first part of which is the definition of evolutionary architecture, which I've just given you. Now I'm going to talk about examples and principles and characteristics of each of these three things: incremental change, fitness functions, and appropriate levels of coupling, both at the technical level and the team level. And then talk about what kind of superpower this kind of evolutionary architecture provides for you by way of hypothesis-driven development in just a bit. So let's talk next about appropriate levels of coupling in architecture. And I mentioned earlier this shift to domain-centric architectures. In many ways, software architecture is fighting yesterday's battle, because you build one or two or a half dozen of these big ball of mud kind of architectures and you say, man, that was terrible. I never want to build another one of those again. And so you get rid of that one and you build a more traditional layered architecture. And this is really great because now I can swap out my persistence layer anytime that I need to. I have a question for you. How many times do you swap out your entire persistence layer in your architecture? Pretty much never. Because once that's in place, there's no compelling reason to swap the entire thing out. But remember when I was talking about where customer lives in the layered architecture? How often do you make changes to customer or these other domain entities? Pretty much every day. And so part of the reason we shifted to this domain perspective on architecture is really just the realization that that's the unit of change that we most normally undertake. Because when you make changes on a software project, you don't make changes just in the business layer. You make changes to customer, which changes the presentation layer and the business layer and the schema and all those things. And so in many ways, you can think of these domain-centric architectures like microservices is taking this layered architecture and is turning it inside out. and making the domain the primary part and embedding the layered architecture or whatever technical architecture you have inside that domain-centric barrier. And we're seeing this a lot. So not only in microservice architectures, which are really popular right now, but the most common migration destination, if you're migrating from some sort of monolithic architecture into some sort of service-based architecture, is a service-based architecture that probably still shares a lot of things around the data, but has shifted things around domain focus within these individual services. And you'll see different variations in service-based architectures of how isolated they are from a data standpoint. But this and microservices are both good examples of domain-centric architectures where the domain is the main unit of change, and we've embedded the technical architecture inside those domains. In fact, what people really mean when they say microservice, in my experience, is a domain-centric service-based architecture with modern DevOps practices. Because most people that are in the process of migrating from some sort of monolith into something like microservices quickly discover that some of the restrictions in microservices, like the data isolation in microservices, is really, really hard to achieve if you're trying to untangle a monolith. And so what you discover is going to domain-centric, but leaving your database alone is often a more pragmatic approach to doing this. You still get the advantages of being domain-centric, but without quite the overhead and the latency and other issues with pure microservices. So really what we're doing here is architecting around the primary unit of change that happens in our projects, which of course is a good idea, because now you can start building teams around that as well. And that's the other side effect of this, is the way teams form around these architectures. I mentioned before that Pat, one of our co-authors, has done a lot of interesting writing around teams and team dynamics. He has a great book out about working with tech leads. And you see a lot of companies that have organized their workforce like this because they're building very frequently layered architecture, so it seems to make sense, well, let's split out all of our workers in layers that kind of correspond to that layered architecture. And in fact, what you're seeing in action there is this idea of Conway's Law, which is an observation that Melvin Conway made back in 1968, which you hear every time you hear a microservices talk. Conway's Law says basically that organizations which design systems end up replicating the communication structures between the humans into the technical pieces of their architecture. This is talked about a lot in the microservices world because we're not building layered architectures in microservices, we're building domain-centric architectures. And so the more common way to organize your teams in microservices is around those domain entities and build cross-functional teams. And so the idea is that catalog will have business analysts and developers and a QA person and a DBA and an operations person on it. Every single person that is needed to build catalog and put it live and maintain it is on this catalog team. Part of the goal here is that every time in your organization right now, you need to do something that you rely on somebody else for. You need a schema change, or you need a database instance, or you need a new server somewhere, or need permissions on a server, or anything like that that you have to wait for somebody for, or the worst case, issue a ticket to someone for. That's what we're trying to kill by this team organization business, because the idea is this catalog team is completely self-sufficient and everything they need is available, so you never wait for a day or a week or a month on some resource someone else owns, because every resource you need is represented on this domain team. This is called the inverse Conway maneuver. The idea being that Conway's Law is going to affect your project whether you want it to or not, so why not embrace it rather than try to fight it? If you're talking to an enterprise architect, you may want to refer to this as domain architecture isomorphism, because you always get extra credit if you can use the word isomorphism when talking to an enterprise architect. But that's really what this is mapping the architecture to the problem that we're trying to solve, which just kind of makes sense. Another side effect of the decoupling that you see in evolutionary architectures excuse me, is decentralized data management. Excuse me, I always get choked up when I start talking about databases. So when you have a monolithic application architecture and a monolithic database, it's really easy to do things like transactions. But when you get to this more bounded context world of places like microservices, the idea is that you don't do distributed transactions here because you don't want to do distributed transactions. And in fact, the microservices world and in general the evolutionary architecture worlds tend to be a lot more base than ACID. And let's talk about that for just a second. We're all, of course, super familiar with the ACID characteristics of databases: atomic, consistent, isolated, and durable. But there are a whole bunch of alternatives to that, usually playing off of the ACID acronym, and BASE is one of those: basic availability, soft state, and eventual consistency is the main idea here. Because it turns out that transactions are a form of coupling, and a really hard to untangle form of coupling. And so eventual consistency is more the norm here. And part of the reason for that, even if you're not doing some sort of exotic microservices architecture or something like that, is that as your system becomes more and more distributed, meaning that you're forced to physically partition your data on more and more physical nodes as the size gets bigger and bigger, you'll reach a certain point where you can no longer guarantee all four of those ACID characteristics anymore. After all, the CAP theorem sort of suggests this, and so a lot of big systems end up at eventual consistency, even if they're not doing some sort of service or microservice-based architecture, just because of the physical constraints of the way that data and physical data representation works. But this, I think, is a big disservice that we've done to our users for many years by making them think that transactions are a natural part of the universe. This just happens to be an easy thing to do if you have a monolithic architecture and a monolithic database, but the real world doesn't really work like that. A few years ago, one of my colleagues famously made the observation that your favorite coffee shop does not do a two-phase commit. Because you can go order coffee, you give them money, and then they give you some sort of token, a receipt, and you go to a different part of the store, and then you eventually get your cup of coffee. So what would an actual two-phase commit look like in a coffee shop? Well, you would hand them money, and they would hand you coffee, and you'd let go at the same time. So that's a proper two-phase commit in a coffee shop. So why doesn't your coffee shop do that? Wouldn't it make you feel better as a coffee member buying of public if you got a proper two-phase commit when you bought your coffee? The reason they don't do that is because it's really inefficient in the real world. They don't want to assign one worker to stop the world in the coffee shop just to make sure you get your coffee as fast as possible. And that's the problem with transactions, is stop the entire world aspects of transactions, which is unrealistic and impractical in many situations. Everybody's favorite example of two-phase commit are bank transactions. But no ATM in the world does what we would call a two-phase commit for two reasons. One is they're all designed to work in offline mode in case their connection to the mothership gets broken. They can still operate, and they do auditing and reconciliation at the end of the day to fix things. But the more practical reason is that no one wants to stand at an ATM for 8 or 10 minutes while your bank stops the entire universe to take your $20 out of your account and then restarts the entire universe around it. Banks always do auditing and reconciliation, usually in the middle of the night, which is why your bank balance changes magically in the middle of the night. You know, banks existed before computers existed, and bank records used to travel on horseback, and there is no two-phase commit when there's a pony involved. So we've got to get away from this idea that transactions are a natural part of the world. Now, certainly some things do act transactionally, but the real point of this is that transactions are a special kind of coupling. They're temporal coupling. That has nothing to do with the way your classes are coupled together with afferent and efferent coupling. This is how things are coupled together in time. And so what we're not saying here is you can't have transactions at all. What it's trying to get you to do is limit transactional context as much as possible, because this is a really hard to fix kind of coupling. This is in fact the kind of coupling that you find most troublesome if you're migrating from a monolith to service-based architecture. Very frequently it's these transactional couplings that are the hardest ones to pull apart, and maybe not even worth the effort to try to pull them apart. One of the things that I alluded to earlier is this idea of evolutionary database design. And a lot of people end up in this particular pattern because it's really easy to do. I need to share some information between two different applications, and they both talk to a relational database. Let's just share that information through the relational database. But then you realize after you've done this for a little while, now you've got a big problem, because now I need to make a change to the schema on behalf of application A, but I can't do that because it's going to break B and C. So I've now coupled them at the data level, and it's really hard to make changes to them. Fortunately, in the Refactoring Databases book by Scott Ambler and Pramod Sattelage, there's a great pattern that gets you out of this particular kind of coupling. Refactoring databases is different than doing code refactorings because there's a transition period. So let me give you an example of this. So let's say that you have this scenario. Balance really should be on account, but it was placed on customer for some reason several years ago, and now application A, B, and C rely on balance on customer, and application A really needs it on account, but I can't just make that change without breaking B and C at the same time. So this is called the expand and contract pattern for database refactoring. This is the transition period for this refactoring. So what I've done here is I've added a deprecation warning to this column. Some databases support this idea of putting a comment on a column that every time you access it, it gives you a warning that, hey, this is going to go away after a certain date. Then I add balance over here, and then I create a trigger on both tables so that now anytime balance is added there, it's synchronized across here and vice versa within the transactional context. I can now support both schemas. I can support the new version of the schema and the old one side by side long enough to get B and C migrated over to this new schema. Once that's done, I can go and finish this refactoring, get rid of the trigger, get rid of the original balance column, and this allows me to actually shift those schemas over time without breaking things. This is talked about in the Refactoring Databases book. This is the expand and contract pattern for doing database refactorings, and this in many ways is the get out of jail free card for we're coupled at the database architecturally. Another side effect of the decoupling that you see in evolutionary architectures is decentralized governance. Now, certainly in the microservices world, one of the things that is considered part of that service-bounded context is what a persistence mechanism it's using. And let's say that you have one of these autonomous cross-functional teams that has an operations person on it and a DBA, and you have a really small service here. And you're responsible for spinning up and operationalizing the database and doing the migrations and all those other things for it. And you've also made the observation that we have very little data. This is a very small service. We don't have any kind of sophisticated querying or anything. And we further made the observation that using Puppet or Chef, we can spin up a working instance of MongoDB in about 1.5 minutes. And I'm pretty sure the first Oracle install dialog won't come up in just 1.5 minutes. Using Oracle for this is like going rabbit hunting with a bazooka. You can be successful, but for some definition of success, it's probably overkill. And so this team may decide, you know what, we're going to implement MongoDB and we'll operationalize it ourselves. And then 6 months later, they realize, oh, this is a terrible choice. We need to replace that with something like Postgres, and nobody else cares. Because nobody else is allowed to couple to the implementation detail inside that bounded context, that frees this team to make whatever technology choices they think is best to solve the problem they're trying to solve. And that's really where this governance picture comes in the microservices world. One of the really tricky things about doing governance in monolithic architectures is that the decisions you make affect everybody. If you pick a relational database or an object relational mapping framework or a fundamental framework that all these things are based on, like Spring or something like that, everybody ends up sharing that same bit of shared infrastructure. And for many of the problems you have, it's overkill. That's really the motivation in the microservices world around this idea of polyglot platforms of right-sizing the technology for the problem you're trying to solve. It's not trying to let 1,000 flowers bloom. What it is trying to pick the right-size technology for the problem, because we've realized that there is no one single platform that solves every size problem. But this can become a big problem in large organizations as well, because you don't want every single development team to have their own artisanal development stack. And so what we see in large organizations, particularly around services and microservices, is what we're calling Goldilocks governance, where you pick a standard small stack, a medium stack, and a complex stack, and you still get the ability to move people between projects, but you are still trying to right-size the technology choice for the size problem that you're trying to solve. And so there's a middle ground between homogenizing, fixing on one platform to solve everything versus letting everybody pick their own thing. This is kind of the middle ground between that. So those are all parts about appropriate coupling at the architectural level. Let's talk about fitness functions. I mentioned this before. This is an objective function that's used to summarize how close a design decision is to achieving its set aims. Fitness here is assessing suitability to task along some sort of spectrum. And a function here is something that returns a quantifiable result, an objectively quantifiable result. So what we're using fitness functions for here is kind of the guide rails for our architecture. And as I mentioned before, these may be things like metrics, they may be things like tests. They're all things that evaluate to some sort of objective answer. And this is one of the problems that we have with traditional kind of non-functional requirements or quality of service kind of assessments, is that there's no way to test them on an ongoing basis. The assumption here in an evolutionary architecture is you have things like deployment pipelines and continuous delivery, and you want to be able to continually assess how well you're doing in terms of meeting your architectural goals. That's why we want to convert all these quality of service attributes into functions so that we can objectively evaluate them on a regular basis. And these can exist at multiple scopes within your project: application scope, fitness functions, integration architecture, or process. And let me give you examples of a couple of these. So integration architecture fitness functions. So one of the things that you want to make sure, if you're in the microservices world, you have these autonomous teams and they're building functionality in their services, and we're trying to allow them to evolve in any way that they want. But they also have to integrate with one another because they need to pass information back and forth between one another. So how can you allow them to evolve independently but still not break those integration points? You have consumer-driven contracts. This is a fitness function in integration architecture in an evolutionary architecture. So the idea is the team on the left is providing some information to all three of the teams on the right. What a consumer-driven contract says is these teams put together a set of tests that encapsulate what they need from this team, hand those tests over here. This team now promises, I will run those tests and keep them green always. Because those tests now encapsulate what they need from an integration point. And so all three of these guys have passed tests over here, and now they're running those tests, those consumer contract tests, as part of their normal build. If this guy changes and it doesn't break any of the tests, then everything's cool because we changed in a way that no one else is relying on. If this changes and breaks one of those tests, that becomes a placeholder for conversation to get those teams together again and recreate those tests so that you can integrate with one another without having to be in constant communication with each other. This is a fitness function for integration architecture to make sure that you don't break integration points. So this is an objectively evaluable function that we can run on an ongoing basis to make sure things are not broken. What about application level fitness functions? So one of the things that you have to worry about at the architectural level in application architecture are cycles. We have a component that relies on another component, which relies on another component, which relies on the original component. Cycles make it really hard to refactor and get rid of bad architectural smells. There's an open source package called JDepend that can analyze your code base and tell you if you have cycles or not. So this is a good example of a kind of fitness function you can define in application architecture, because one of your goals may be, I don't want cycles in my application architecture. This is an objective way that you can evaluate that. And in fact, JDepend will even let you go broader and define some rules at the architectural level about how you want things, directionality of imports within your architecture. So those are examples of application level fitness functions. You can also have process fitness functions for things like how long my cycle time is, or any kind of measurable process evaluation. Here's a fitness function spider graph that we did for one of our projects. Pretty much any of the entities that we've traditionally tracked can be tracked using this with fitness functions, and that's really where those kind of quality of service things end up in our architecture. Notice what we're trying to do here with fitness functions is guide our evolution. I suspect that you could create an evolutionary architecture that models real biology, an architecture that just randomly changes one of its bits and then redeploys itself, and in a few million years you might have a really interesting architecture. We don't have a few million years to wait, and so we're guiding evolution just like we guided the way dogs look now. We've done that to dogs over the last few thousand years. So we're trying to create breeds of dogs here, not trying to create platypuses. So where does this all end you up? So there's a great podcast called Radiolab that is not a tech podcast, but rather just a regular news podcast. And they talk about, there's a great story here about this idea of hypothesis-driven development. So it turns out that Facebook had a really big problem. Between December and New Year's Day of 2013, people uploaded more than 1 million photos, actually way more than 1 million, more photos than Flickr had to Facebook in that small period. And more than 1 million of those was flagged as being inappropriate. And they couldn't figure out why they were being flagged as inappropriate, because when they looked at many of them, they were not things that looked inappropriate at all. But fortunately, Facebook has the ability to run experiments against their users and create this thing called hypothesis-driven development. So when you have building blocks like continuous delivery, like modern DevOps practices and the ability to put things live side by side, things like feature toggles, which gives you the ability to switch things on and off on a really, really controlled basis using a toggle router. This is a well-known practice in the continuous delivery world. That, and then plus evolutionary architecture, what that gives you the ability to do is this idea of hypothesis-driven development. So here's the idea. So what you're doing right now is cooking a buffet. You go in the back, you come up with recipes, you cook all these dishes, and then you lay them out for your users to consume. And some of your users love the things that you're cooking, and some users treat what you're cooking like vegetables. So what if, rather than cooking the entire buffet, we could give them just a taste? So that's this idea of hypothesis-driven development. You still have vision and strategy and business goals, and you build a minimum viable product of whatever your product is out there, or you take what's running out in the world. But now, instead of building new requirements, you instead come up with hypotheses. Here's a hypothesis. I believe that if we increase the image sizes 15%, we'll get more people booking cars on a car website, for example. That leads you to a portfolio of ideas, and from that portfolio of ideas, you select some experiments to run. Maybe one of them does some of the things that your users like, but not everything. This is the classic pivot, where you pivot and just change what you're doing, but keep the main thrust of what you're doing the same. Maybe one of the experiments you try looks really promising, but as soon as you try it, you get no engagement at all, so you can kill that. And of course, what you want is one of your experiments to be really, really successful, and you can double down on that and put more and more resources into it. What this really allows us to do is fix a problem that we've had in the Agile world for a really long time. Agile software development is about feedback loops, but it's really about nested feedback loops. Because you look at any Agile methodology, that's what it's really relying on, these nested feedback loops. But there's one feedback loop that has eluded us forever, which is the one all the way out to the user. And that's what hypothesis-driven development gives us back, is the ability to reach out to our user and learn things about them as well. Get them in the feedback loop that we've been in for a while, and it allows us to build more things that they like and less things that they don't like, because we're being a lot more adaptable about what we're building. And that's a lot of what this evolutionary architecture is about adding adaptability as an ility in architecture, along with scalability and all the other ilities that we think about in software architecture. This is going to be an ongoing problem, because this dynamic equilibrium problem is never going to go away. In fact, it's going to get more and more acute over time. And so that's why we believe it's worth spending some time learning about how to make architectures more adaptable. And that is, in fact, what we're doing research on and writing into this book. We're making progress on this book now. But as we're writing this book, we're also publishing a lot of stuff along the way. So Rebecca and I have written a microservices as an evolutionary architecture article on the ThoughtWorks Insights page. A lot of our stuff is going to be published here on the ThoughtWorks Insight page. We're also doing some podcasts around this. I've done some podcasts around DevOps and microservices. I also just recently did a podcast around this definition of evolutionary architecture. So we're going to keep putting our stuff out into the world as we're working on this book. And we're going to try to get this book done as soon as possible. And in fact, I'm going to stop talking now and go start working some more on this book. And I've reached the end of my time, so we're now on a break. Thanks very much for coming, and I hope you enjoyed it. Thanks.